All right, now organic molecules are a little different than what we talked about. So first of all, how do you know if you have an organic molecule? Organic is the study of carbon. Okay, some of you are going to have to take organic chemistry. I teach the organic chemistry here at Front Range. So some of you are going to have to take organic, and basically these I think are a lot easier. So the way you know you have an organic molecule is you have carbon, but it's not just carbon, it's carbon and hydrogen. Because there are some molecules that just have carbon, like CO2, for an example, has carbon but no hydrogen. This is not really considered an organic molecule. You really have to have carbon and hydrogen on your molecule. All right. In this case, carbon is always your central atom. It doesn't matter what other atoms you have. And carbon always makes 4 bonds. All right. And they could be single, double, or triple bonds. Okay, so pretty much like if I have a formula CH3Cl, all right, carbon's my central, you have all the other atoms around it. You don't have to do the valence electrons and all that stuff because you'll always make 4 atoms, all right, and everything has to still be octet. So your carbon will always be octet as long as you make 4 bonds. Hydrogen always has 2, and then whatever atoms you have around it, just make sure it's octet. So I have to put 2 lone pairs for the chlorine. All right, so organic molecules are much easier. Here's ethane. Ethane is C2H6. All right, so in this case, you will have more than one central atom. Okay, for organic molecules, all of your carbons are linked together. So you have a carbon attached to a carbon attached to a carbon, and then everything else is around it. Okay, that's a organic molecule. So in the case of C2H6, you'll have 2 carbons. Remember, I said you have 4 bonds, so you're going to have all your hydrogens around it. Okay? What if I had something like C2H4? All right, let's do that. 2 carbons. Let's put maximum hydrogens. What you should get in the practice of doing is making your molecule as symmetrical as possible. So if you have something like C2H4, you know one carbon is going to have 2 and the other carbon is going to have 2. Don't put 3 on one and 1 on the other. Try to make it as symmetrical as possible. So I've accounted for all the atoms, but notice, what do you notice about the carbon? It's not octet. So how do you make it octet? Coordinate covalent bonds. So with organic molecules, you're not going to be putting lone pairs on the central atom. You're just going to be making double or triple bonds. So if I have like C2H2, all right, I have a carbon attached to a carbon, make it symmetrical, 1 hydrogen here, 1 hydrogen here. Well, the carbon needs to have 4 more electrons, so make it into a triple bond. Okay, all your atoms are accounted for and everything is octet, with the exception of hydrogen, which has 2. And that's organic molecules. I hope that wasn't too fast. You might be thinking that's really easy, and yes, it is really that easy. That's all you need to know for organic molecules. Okay, so let's just do a practice problem on CO2. Like I said, CO2 is not an organic molecule, but this is just another practice, just a practice to actually do. So CO2, carbon has 4, each oxygen has 6, so that's 12. This equals 16. There's an important concept in here. So carbon, so notice you have 8 on each one, so a total of 16. All right, I don't have any left over, and notice my central atom is not octet, so I gotta make coordinate covalent bonds. So one of these lone pairs will go in here, okay, to make a double bond. I still have 2 lone pairs. It doesn't really matter where you put the lone pairs. Notice my oxygen's still not octet. So what do? Do I take a lone pair off of here and make a triple bond? Yes, you could. Or do I take a lone pair here and make a double and a double? Well, if I do this, remember the last slide I told you, you want to make your molecule as symmetrical as possible. So this is the more correct way than this way, though it's not incorrect. This is what's called a resonance structure, but technically this is the way to do it because you are more symmetrical. All right, so this just kind of talks about how to do it, okay? All right, now here are exceptions to the octet rule. There are exceptions. There's always exceptions to the octet rule. We're going to talk about, it looks like 3 of them. I'm going to talk about 3 of them, okay? The first one is odd number of electrons. I don't know if you realize this, but every example we did, there's always an even number. And you should be thinking to yourself, well, why is there an even number? And you should realize, well, everything is pairs of electrons. Pair, 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 pair. So you're always going to have an even number. Well, sometimes you might have an unpaired electron, like in this case. And this happens with nitrogen. Nitrogen is known for having unpaired electrons. These are what's called free radicals, by the way. You've heard of free radicals. That's why you take your vitamins and drink juices and stuff like that to clean up all the free radicals in your body. Electrons don't want to be unpaired, so they'll do whatever they can to be paired up. Okay, so nitrogen is notorious for this. So how does it work? Well, or how do you combine it into your drawing your Lewis structures? Is whenever you have an odd number of electrons and you have nitrogen, nitrogen will be your central atom. All right, and your nitrogen will have 7 electrons around it rather than 8 with an unpaired electron. So in this case, this is NO. I believe. Let me just make sure. 6 and 5, 11, 2, 4, 6, 8, 10, 11. Yeah. So it's NO. So you have a nitrogen, oxygen, maximum electrons on your outer atom. Any remaining go as lone pairs on your central, with the exception of the odd number. And then you try to get this to 7 or try to get this to octet. So you're going to erase a lone pair and make it into an octet. Okay? So just be aware of that. If not every nitrogen is an odd number, like we saw NO3 as one of our examples, that was not an odd number. Okay, so please be aware of that. If you have an odd number of electrons and you have a nitrogen, you're good. If you do not have a nitrogen and you have an odd number, you probably miscalculated something. All right, so that's kind of a good check. The next one is beryllium and boron. Really the major one I'm going to focus on more on is boron. Boron is happy with only 6 valence electrons. Okay, notice this boron has 2 here, 2 here, and 2 here, 6. You would not make a coordinate covalent with boron. So if you have a boron, let's say you have like BCl3 or something, your structure is going to look just like this. Okay, just like the BF3, but you have chlorines. All right, do not make coordinate covalent bonds on boron. So boron, really, you're going to do steps 1 through 4. You will never do step 5, which is make coordinate covalent bonds with boron. Okay, in fact, you probably won't even get to step 4. Step 4 is any remaining electrons on central atom. So now that I'm thinking about it, it's really just steps 1 through 3. That's it for boron. And I guess technically for beryllium too. Okay. And then lastly, it's something called the expanded octet rule. There are atoms where you can have more than 8. More than 8. Phosphorus, it's usually phosphorus and sulfur. These are atoms that are in a d that actually have a d orbital accessible to them. So it's things in n equal 3 to 7. All right, because remember in 3s you can have a 3s, a 3p, and a 3d. You can't have any d's in the 1 and the 2. So it's really for anything that have a d orbital accessible to them. They can have what's called an expanded shell rule. They can expand their shells to allow more electrons. Phosphorus is notorious for having 10, and sulfur is known to have 12. So just be aware of this. Don't get freaked out when you see this. We're really not going to worry about many molecules that have an expanded shell rule. So don't just automatically, say to yourself, well, how do I know you have it? Well, none of the molecules that you'll have to draw will have it. If I have a molecule, I'll put like a molecule right here, and the question might be, why does sulfur have 12 electrons around it, when clearly the octet rule is the major rule? And you'll say, well, because of the expanded shell rule, sulfur has a d orbital, and it can allow for more electrons. Okay, so just be aware of this. You won't have to really deal with it when you draw molecules. All right. Section 6.3 is about resonance. What is resonance? Resonance is when you have 2 or more equally correct Lewis structures. All right. So here's ozone for an example. Well, actually, let's use the nitrate example, because this was the first example. Remember when I drew the molecule, I drew it like this. I had the lone pairs. And I said you can use any lone pairs you want. So if you wanted to, you could have drawn it like this instead. Used the lone pairs on that oxygen instead. All right. Or you could have used the lone pairs on this oxygen. I'll draw it over here. You could draw this molecule also Well, these molecules are equal. They are equal in stability. They are basically the same structure. It's just you're using different electrons to explain the same thing. Okay, notice it differs only in the placement of the electrons, not the atoms, just the electrons. So if there's more than one possible structure, notice in the CO3, this is CO3 2 minus case, in the carbonate case, double bond is either here, or you can put the double bond here, or you can put the double bond here, but these are all the same molecule. And that's what resonance is. So how do you know if you have resonance? I'm gonna make it very easy for you. If you have a double or triple bond, you have resonance. That's it. That is all you need to know. Double or triple bond, you will have resonance. All right. Remember in the CO2 case, remember we had either this molecule or I showed you you had this molecule. That is also resonance. All right. Basically, this double bond came over here to give you a triple bond. Okay. So that's what resonance is. Don't go more into it. There is a lot more to it. If you do take organic, we definitely talk a lot more about resonance, but this is all I want you to know. If you have a double bond, here's ozone, there's a double bond, it could be on either side. So your molecule is going to have a resonance structure. Okay? These are just doing some Lewis structures and determining there's resonance. So here's the structure for SO3. Does this molecule have resonance, yes or no? Hopefully you answered yes because you have a double bond. You can draw the double bond here instead, all right? Or you can draw the double bond there instead. So yes, there is resonance. Here are the 3 resonance structures, okay? So that's the end of the video for 6.2 and 6.3. And when you come back, we will start getting into molecular shapes and section